Hello and welcome back. So today I'd like to talk about memory. Now I first put memory in my processor build in part 7 and this was it. An 8028C16 which is 16 kilobits, 2 kilobytes ROM. So I've been using my trusty programmer to stick data on there. It gave us a way of developing and testing some code. 2 kilobytes is probably going to be limiting, so I'd like to get a bit more memory in there, and most importantly I'd like to get some RAM. So I have the 8028C256, which is 256 kilobits or 32 kilobytes of ROM, and I bought some of these. These are AS6C62256. Now, the main reason why I selected these particular chips is there is both an SMD and a DIP version of it, so I can build with the DIP version on breadboard and switch to the surface mount device on PCB. Okay, let's take a look at this ROM chip first. So this is the 8028C256. I don't think we need to spend too much time looking at this because I use these on the pipeline already, and the pinout on this is very similar to the 8028C16. So the data lines are in the same location, relatively speaking. Ground and VCC are in opposite spots, but then you've got the first 8 address lines in a row here, but then the control lines and the upper address lines are swapped around a little bit. Now this is the RAM chip, and if you look at the pin configuration here, you'll realize it's basically identical to the ROM chip. The address lines are all in the same location, as are the data lines. Chip enable, output enable, and write enable are in the same place. Now the operation of the write enable line is different. It's much simpler on the RAM chip as you'd expect, but since we don't use write on the ROM chips, this is the one we have to worry about. So read, it's pretty much the same as the ROM chips. We stick the address on there, and if output is enabled and the chip's enabled, the data pops out at appropriate time interval afterwards. But these write timings are what's going to interest us a bit more, because we've got some more complicated signals to worry about, and we've got to generate these from the signals that we've already got on the processor build. So here's our 2 chips. Now I've clustered the lines out neatly so we can take a simpler overview of it. Let's first look at the signals that we've already got on the processor. So we've got a clock line, and just the same as for the registers, we've got a load line to the memory device, which is where we want to perform the write. Now this goes low at the start of the cycle and returns high when the data is supposed to be on the bus. Now at the same time as that, we've got the address will appear on the bus, so we'll have selected that from the final pipeline stage, and the signal will go off to the address register that's relevant, and it will assert its value onto the address bus. So I've kind of faded this in a little bit to say we're not really sure when that appears, but it should be fairly quickly, and then it will remain there for the remainder of that cycle. The data will be the same. We have no idea what device is writing to memory. It could come from anything that's hung off the main 8-bit bus, but the only thing we've ever said before is that the cycle is kind of divided into 2 halves. So we'll get a device assert command, and it's kind of got the first half of the cycle to get the data onto the bus, whatever device is going to assert, and this kind of dividing line when the clock drops back to low is when we expect the data to be there. In most cases though, data valid is going to be pretty much the same as address valid, because it's just register data that's being pushed out via a line driver. We've also got this memory direction line. Now the main use for that is on the memory bridge to decide when to pull data from the main bus onto the memory data bus. But we're also using that already through an inverter into the output enable line of our 2 kilobyte ROM, because we need to tell the ROM not to output. Otherwise we're going to get a horrible clash on the memory data bus. Right, let's have a look at the write timing again. Now I thought I might have to build a circuit to generate the write line. But the write enable is an active low line, and so it already looks quite a lot like our memload line. Let's have a look at the rest of the timing signals and see if there's anything that's going to cause a problem. This TWC is the time the address needs to be valid for. 55 nanoseconds, well, we're going to cover that no problem. Now, at the moment, if we have the end of the write enable line in the middle of our cycle here, then TDH needs to be half our cycle, and that's actually 0 nanoseconds. So we don't have to worry about that at all. In actual fact, this rising edge could be much further towards the end of the clock cycle and we'd be fine. So TWP is the time it needs to be low before coming high, 45 nanoseconds. So this will work as is, but that is immediately posing a maximum clock rate restriction on us of, well, roughly 20 megahertz, so that's never going to be a problem. And this TDW, okay, this is interesting. So data to write time overlap needs to be 25 nanoseconds. Insofar as we have a specification so far, we've said that data needs to be on the bus by the midpoint. And it might be delayed very slightly by the memory bridge because that's onto the main bus. So now every circuit we've got at the moment, that's going to work fine on, but I'm going to have to factor that into my calculations for trying to work out the maximum clock rate, because I think that might pose more of a restriction. What we could do here is push the rising edge of memory load back a bit, because if we can knock that 25 nanoseconds back, then we're conforming exactly what we've said elsewhere in the processor, and it will not impose any extra restrictions. I don't think this is actually an issue at all, because the data's probably going to be settled on here at any achievable clock rate, but it's worth considering that. So right now we're probably, rather than running at a maximum of 20 megahertz, we're probably capping at ourselves somewhere between 5 and 10, depending on the latency of getting data onto the bus. Now we know the counter address registers are going to cap us at about 4 megahertz, so I'm not worried about this. Let's think about the wiring. So we've got a memory load line, a memory direction line, 8 data lines and 16 address lines. These chips have 15 address lines. Data is going to be easy. We can just wire that to them both. And the first 15 address lines, we can do the same. Now what we need is ROM and RAM to be enabled via the chip enable line at different times. Now we start executing at address 0, so it would be good to have the ROM at the first half of memory and then the RAM in the upper half. This is active when the chip enable is low, and in the lower half of memory this top address bit will be low, so we can just bring that in like that. And then the RAM chip, we want the inverted form of that. I should probably mention at this point that I'm very slightly worried about a possible contention issue here, because this does mean that the latency of this inverter is going to be a potential overlap between the output of one chip and the output of the other. Looking at the timing diagrams, I don't think that's an issue, because both these chips will take their data off the line quicker than they'll put it on, and the inverter chips are very quick. But this is something I do want to keep an eye on, and maybe I'll poke it with the oscilloscope to see exactly what's happening. Now, one possible alternate solution to this would be to use a 3 to 8 line decoder. Now, their primary use is actually in this kind of chip enable situation, and that would give us 3 address lines to select up to 8 chips. Now, my original plan for memory was actually to do that. I was thinking maybe having an 8K ROM and then 7 8K RAMs, but that's not going to work because nobody really makes RAM and ROM that size anymore. 32K is about as small as they come in kind of brand new modern parts. So I'm going to stick with the 50-50 split. Now, I would at a later point like to look at a couple of techniques for giving me a bit of extra RAM and maybe making the amount of ROM flexible. And so I will come back to memory at some point. Right, output enable, we already did this when we did the memory bridge circuit. So that's the memory direction line inverted. And then we have to worry about the write enable lines. Now already with the existing memory, we've just tied that high on the ROM. We're really not interested in doing anything with that line on a ROM chip. But on the memory, we've already talked about the mem load line basically matching what we need. Now we could talk about ways of pushing this rising edge back. Now one way I could do that is by building a simple circuit to delay this signal, and that would completely eliminate any restriction on our clock rate coming from this. It's not necessary, but we've got two inverters here and they come 6 on a chip, so I could do that. Use the 4 remaining inverters to push this load line back. I don't know if that's the right way to introduce a delay or not. I'd appreciate some comments on that, but it's certainly not anything we have to worry about now, and maybe we'll have a different use for those inverters when we come to actually design a PCB for this. But you know, if you've got any thoughts on that, comment away. Okay, let's try and build this thing. Now you've seen me struggle with fitting the ROM chip in and out on the main build, so I'm going to try and put this ZIF socket in. This is going to be a tricky wiring job, trying to get all the 28 connections in quite a limited breadboard space. I did get a shorter breadboard with an extra row in that David Watts recommended to me, but I figure I need the length, and one extra row doesn't make it a lot easier. It's just going to be difficult. I'll use a socket for the RAM and the ZIF socket for the ROM. Now I'm going to use these 8-way DuPont cables to get the address in and out, and so the first 8 address lines are in a row here, but the others are kind of spread around, so I'm going to try and bring those out to a common location. There's good, and leave one space for the RAM chip. Power and ground for those. Just checking the pins at the bottom do line up with the holes at the top. And we need an inverter, so this is a 74LS04. Okay, so this is the connector board at the bottom of bus control at the moment. So I've got this 5-pin connector, so I'm going to make up a fly cable to plug that in down here. I need to connect the wires up to there. So I think what I'll do is I'll try and bring out all the wires from one of these chips, or at least all the common ones, address and data, get them all in a row. So 8 data lines here, the lower 8 address lines are already in a row here, and then we'll bring the upper 8 address lines in here, and then I'll try and cross connect all of the relevant pins between the two chips. Actually, I can put the connection for write enable over here and pull it high, just like we did on the original board. So let's worry about the data lines. It's kind of odd because we've got 0, 1 and 2 here, and then the next 5 over there. If we use those 5 in a row and bring these 3 across. Okay, so that's the 8 data lines in a row. And we need to do the same for address. Address line 8 first. 9 is next to it. 10 is further down, but 11 comes out over here. 12 and 14 come from the other side. 15 needs to come over here to chip enable. Okay, we need to take 15 across to one of our inverters as well. I've already blocked that away. Should have done this one first. Get that 13th line in now. Line 10's fairly straightforward. 12 and then 14. That doesn't look too bad. Okay, let's assume this will come in like that, and then that will connect onto the memory bridge like so. I just grabbed one of these PCBs for reference. So let's actually connect the ground line up. So Then we need the direction line into another inverter. And that goes off to output enable. Is that right? Yep. Want that inverted address line to go to chip enable. And last but not least, we need the write enable line, which is load line from here. Bring that all the way across to write enable. Alright, this socket isn't sitting down as well as I'd hoped. Really don't want any risk of loose connections there. Right, I've trimmed off bits of these turn pin headers. Shouldn't be anything stopping us from fitting our RAM. Then ROM can slot neatly and easily into the ZIF socket. Now all we have is 25 lines to connect from there to there. Now I have made this wire form. The idea behind this is the distance, or this groove, the centre of it is the distance between the comparable pins on these two chips. So if I wrap a wire around there and then cut it and trim the ends off, it should be the right length. And I'm hoping this kind of 3D structure with a little bit of a rise will give me the flexibility to get these wires connected. I'm going to start with the data lines here. There's 3 of them on this side. And 5 at the top. These wires aren't quite as identical as I'd hoped after making the form, but it was actually quite a lot quicker to make them than by measuring manually. So I might do more forms for this kind of stuff in the future. Okay, so then got the 8 lower address lines, then 2 random higher ones. Okay, now on the top side we've got A10, which kind of sits out on its own, leaving a gap for chip enable. But then we've got the output enable line. I've actually successfully kept some commonality of wire colours here. And then we've got 4 more address lines. Okay, I actually think that looks surprisingly good, considering how many connections there are. Okay, we do have some unused inverters. I want to resolve their inputs. Let's go like that. And I think that's done. Oh, spray some decoupling caps in. Okay, I'm pretty happy with that. Okay, now I'm quite keen to give that a test. So it won't be very long for you, but I need to clear up and get the main processor build back out. Okay, I've got the build back out. I was very pleased to see it still working. We've still got a bunch of that ground noise, which I'm hoping will be resolved a lot more by the new PCBs I've got planned, but hopefully it's going to stay down at a level where it's not causing a problem. So here's the new breadboard we've just made. Now I need to extract memory from over here. Right, so the inverter here was the chip enable line. So during a write operation, it's not outputting from the ROM. We don't need that anymore. Let's turn this off. Now, these wires were basically bodges because this DuPont cable was one of the first ones I made and it's not very sound. And this is the 8 bits of address bus we're currently using. And we can retire this ROM. The memory bridge componentry we will leave here. I'm going to be transferring this onto PCB sooner rather than later, and then we'll just leave the memory itself on a breadboard until we've finalised it. We can chain the connections in for the memory bridge to there. So this actually already has ground directly from here. It does need power though. Okay, I've just realised I've made a mistake on this board. I intended to leave a row spare for the connection of the data lines, and I don't have it. Be right back. Okay, I've managed to move this down a row. I had to cut new yellow wires, but the blue ones I managed to just reroute. So I can put that back. That looks good. Okay, so now I should be able to get the data in here. And that's the low 8 bits of the address bus. And this should be the high 8 bits, which we've never really tested before. Okay, swap those around. Okay, in theory, that should work. So I've already programmed onto the ROM here the same code we were running before. Okay, that's not working. Hang on. Okay, what's going on? I'm not getting any instructions read in. Expect this to be alternating quickly. A bit slower. Okay, so that's definitely getting what looks like an address come through. So we expect chip enable to be low. This line here, which it is. Output enable should be low, which it is. Alright, let's look at these address lines in detail. It's kind of difficult for me to get this in a position where you can see it, but I'm going to read first 8 address lines. So we're on to A11, 11, 9, 8, 13. It's not responding. This blue wire here is 13, and that's going in the wrong hole. Question is, did I do that correctly and then mess it up in my hasty rework? Okay, that's good. We were just reading out the wrong address because one of the lines wasn't connected. Now we can put the RAM chip back. Okay, that's cool. A new board is in and it's at least doing what the old board did. And we've got 32K of ROM we can play with now. In theory, that RAM chip should work, so let's take advantage of our easy to remove ROM chip and see if we can write some code that uses it. Now, RAM starts in the upper half, so I need to get a pointer to that. I need to write a better way of loading a 16-bit address into TX, but that can be saved for a later date. I'm going to start A at 1, get the address in there, and let's try storing A, increment SI, and shift left A. So we do that 4 times. Let's move SI, TX again. And then we'll load those values into A, B, and C. I'll leave the old test code up there because I'll probably want to come back to it at some point. Okay, so first instruction, move TH, 80. Yep, we're moving TL, 0. It's not going to change anything because it's initialized to that. We're moving A, 1. Let's move TX into SI. I should actually be using DI for that by name, but it will work, I hope. Okay, so then this instruction is going to store A into the address of SI. Okay, I was kind of expecting that LED to be on because the memory bridge should be pulling the value across, and we did test that worked. We have this line on load, not on the direction line. That cable was loose, no worries. That's not good. It's only a display though. Right, so here's the shift left being dispatched. That's worked. It's the increment to SI, which should be followed by the next memory write. We can probably just keep going for this for a while. Right, that's our first memory load. So we should be back at the first byte of RAM. So this should put the value of 1 back into A, which it definitely hasn't. Oh, memory read, it happens up here. Okay, well we've got 4 there. Let's see what happens when we go on. So that's the increment again. Here's the load of B, also 4. Okay. So then we should be loading D. Okay, this definitely seems like we're doing something with memory because we've read in 2 of the values we wanted. I'll spare you this bit of troubleshooting. The problem wasn't memory related, so the new module we've built today is fine. It's a slight error in the way addresses are calculated, and so I'll deal with that at the start of the next video. For now, I just fix it in software just by moving instructions around slightly, and then we can see how the new hardware is working. There's the 1, there's the 2, 4, and that's already got 8 in it, but we should see it get loaded anyway. Fabulous, that works. Okay, what we now have here is a Turing complete processor. We've got a fully operational ALU. The pipeline can drive all the registers in the memory, and we can store a program. We could construct programs in the RAM if we wanted to and execute them. It gives us a tremendous amount of flexibility. Okay, in the next build video, I'm going to try and expand the functionality a little bit because whilst we are Turing complete, some operations would be a real pain at the moment. So I'm going to implement some stack related operations, which means we can write simpler code to manipulate more data than we've got in the registers. So that's going to be cool, but I'm really chuffed with this. The memory system is working. We've got RAM and ROM in there. Using this ZIF module totally makes this a lot easier. I totally recommend using one of those if you're building anything like that. I hope you've enjoyed this. Very rewarding for me. I'll see you again soon. Goodbye.